Hello, hello, hello. I'm just going to do a quick breakdown of this combined cloud atmosphere shader that I've worked on for quite a while. This is probably not my final iteration of it, but it is a functional iteration of it that I think is usable at this point. You can see we have a nice atmosphere around our planet. We have planetary shadows on the clouds, and we also have seamless transitions from space to ground, as well as things like scattering influence on the clouds, color, and things like that. So I'm going to include, when I put this on YouTube, I'm going to include the code. Uh, but I can go ahead and scroll through it real fast. I'm not going to break down all the code, but I will just pull it up on the screen and scroll through the actual shader code. So we're just setting up all our values. I'm just going to slowly scroll through the whole thing so that anybody who wants to can pause it at any given point to find that section of code. So we have two sphere intersection methods that are used for different reasons. We have this get cloud trace segments that returns our cloud trace line segments. Our height coefficient allows us to create a fall off based on the elevation of the clouds. Shadow factor is the shadow cone of the planet calculation. Hinye-Greenstein is a phase function that we use. Let me make sure. Okay, so far nothing's been off the page. Sample cloud density. So this is what's actually doing our texture sample of our volume textures to see what density we have. So I'll go ahead and scroll over here so that you can get the whole thing on screen. All right. Light March is our light march function for our cloud shading. Cloud March is our density marching function for our cloud shading. And again, it goes off screen, so we'll just go ahead and do this so that you can get the whole line. Accumulate clouds is what combines those two together and finally gives us our cloud accumulation value. We got an atmo out struct just because we need to return two float threes from our atmosphere scattering calculation, which is right here. So this is doing our actual atmosphere calculations here, and this is an MIT licensed shader that I adapted from GLSL on ShaderToy, which is a website where people upload various GLSL shaders. And so I just converted this to HLSL and basically adapted it to work in Unreal. Skylight is a part of that atmosphere function. Camera altitude ramp is used when we're determining the scattering fade in for the clouds. And then we have our main image function, which actually composites our atmosphere, cloud functions, and whatnot into final scene color. And then I will mention when you're doing these for Unreal, if you want a function library, you have to wrap your functions in a struct, which is why we have a struct wrapper on all of our logic here, right? And then we initialize that struct. We initialize all of its parameters based on parameters that are passed in through our function. And then we return the main image function, which does the compositing of everything else. So this is the code. You can kind of see everything that's going on if you look at this in a little bit more depth. And I will paste this on. I will paste this in the description of the video when I post it. Next up, let's pull up the material. So, to content drawer, cloud atmosphere. Here's our material. All right, so how do we take that code and make it work in Unreal Engine? Well, to do that, you're going to need to build this material. So this is the code that we just looked at. This is a custom node. So you're going to want to create a custom node. And then into this custom node inside the code section, you're going to paste the entire contents of the code that I just went over. And then once that's done, you're going to need to add a ton of inputs because we have a ton of inputs here. And I'm going to zoom in and we'll talk about each one, right? So this is a post-process material, which means that you're going to need to go into your material and change it to the post-process domain. All right. Um, I believe I may have also changed the. Oh yeah. So the other thing that you're going to want to make sure is that your blendable location is set to translucency after depth of field, and then also your project settings. It will bug out under certain anti-aliasing methods. So you can't use TAA, and we'll take a look at what that looks like. Or maybe you can. You can use TAA. I think at one point it was jittering, but I may have fixed it. So yeah, you can use TAA. It actually seems to be working in all of them right now. So I guess use the one you are most comfortable with, or the one that your project wants. But if you have any kind of weird graphical glitches, I would try messing around with the anti-aliasing settings. So going back into our material, really the only thing you got to do to get this thing working is paste that code in a custom node, add all of these variables. So just to start, right? You're gonna need screen UV, and these have to be if you're using the code that I pasted, that I'm going to paste. You can see down here where we set all these variables. They're coming from these lowercase into the uppercase like instance variables that we're using in the whole thing, right? So you need inputs for every one of these that are listed here. And what that ends up looking like is this. So they've got to be named exactly the same. If they're not named exactly the same, it won't work. So you've got screen UV. Screen UV in a post process is your basically your pixel index, right? So all you need for that is just your text coordinate, just a regular text coordinate node. Plug it into screen UV. You're done. Next, camera position. Camera position node. Plug it into camera position. Easy. Next, camera vector. Camera vector node, normalize, plug it into camera vector. Next, you're going to need a planet position node. This is going to determine the center of your effect. So this has to be passed in externally. So if you have a planet at a given point, then you would need to pass this in externally based on your planet point. But right now we just have it set to a vector of 0. So our atmosphere is centered on 0, 0, 0, right? So planet position, light position. Just like planet position, this is going to determine the direction of all your lighting and things like that. Going to help determine the shadow cone on the clouds themselves and things of that nature. So right now my light position is by default just a very large number off on the x-axis. But if you have a star in your scene, then you would need to set the light position to be the same as the position of that star. Next up, light intensity. Light intensity is just a scalar value. You can set this based on how bright you want your star to be or potentially how far away the planet is. And you can go and play with these in the material instance, which we will do after I go over the material setup itself. So we got light intensity. Next, we got planet radius. So the planet radius defines the innermost starting floor of the atmosphere. So this is like, where do we transition from it being a planet into there being atmosphere, right? So for our in editor view, we have that set to 160 here, but it should be set to whatever your actual planet's minimum radius is. If you have like a varied elevation, you would want to go with whatever the minimum elevation is that the planet can have. All right, next. Scene depth. Okay, so I had a lot of trouble getting this to work. You can't just use a scene depth node. The way I ended up doing it, and it's still not perfect, but it's the best one I've found, is you want to take your camera. This is a length, so it's just, excuse me, it's going to be an absolute value regardless. Um, so you could subtract these in any order, it doesn't really matter. But right now we have our absolute world position of the point we're sampling on the screen. So like it will take, like if I was sampling this point, it would give me the world position on the sphere. We subtract it from the camera position, and then we get the length of that, and we pass it into the scene depth input. So camera position, absolute world position node minus camera position node ran through a length function plugged into scene depth. Then also take the world position node and plug it into world position. Pixel normal is the world position normalized, put it into pixel normal. Next, scene color. Excuse me. Scene color is a scene texture node set to post process input 0, put a mask for RGB on it, plug it into scene color. All right. So these are the, I would call them like derived or external values. Things like planet radius and planet location and light position are all things that are determined outside of the atmosphere itself, right? Like we know we need to know these things in order to be able to generate the atmosphere in the first place. And then also things like derived values that are coming from just like existing nodes and things. Kind of most of the derived and external values end here. So next we've got cloud color. Cloud color is just a color input. Name a color input, plug it into cloud color. Cloud height, this is how high is the limit of our cloud rendering here. So we'll just put it back to 10 for now. But this is like how high off the ground do the clouds start. So if I did this at like 15, then you can see that the floor of the clouds is raised up a bit. If I do 20, you can see it's raised up more, right? So this is controlling how far off the planet's surface your clouds are. We'll just put it back to 10 for now. All right, next, cloud thickness. How thick is the cloud layer in total? So if I were to do like a 2, our cloud layer is a lot thinner, and it's not going to look super great in the editor here, just because of the fact that it's not really big enough. But you know, it is what it is. So this is how high off the ground are the clouds, how thick are the clouds. Cloud step scale. This is changing the scale at which the steps occur. And then cloud density steps is actually a little bit of a misnomer here, but it's a divisor figuring out how many slices we're going to do for a given distance. So you can play with these values to see what the effect is. By default, I have it set to 3 and 64. You can, again, play with any of these values and you'll be able to see what the difference is. Next, cloud light steps. So these are controlling our steps determining the density of the cloud itself, and these are the steps towards the light from each density point to determine the lighting of the clouds. I'm using 6 here. It seems to be fine. Anything between like 4 and 6 seems to be fine. You want to be careful because it's a nested loop. So it has a substantial impact on performance, and past a certain point, you're only going to get marginal benefits. Okay, absorption to cloud, absorption to light. These are your cloud absorption parameters. You can mess with these and kind of see what kind of different effects they yield. But generally, I have the default set to 0.7 and 0.3, and we'll look at these a bit more when we go and actually mess with the material instance. But if we come over here, we can see we're plugging cloud step scale, cloud density steps on these two that we looked at. We're plugging cloud light steps likewise into cloud light steps. We're plugging cloud absorption to cloud and cloud absorption to light in the two absorption values that we just talked about. Cloud G is the G value for our phase function, the Henry-Greenstein phase function. It plugs into cloud G. And this changes like basically the scattering direction of the light. All right, next, cloud darkness threshold. A little bit out of order here, but cloud darkness, let's do this. There we go. There we go. Cloud darkness threshold, you can mess with this and it will change the shadowing and lighting on the clouds as you change this value. And we plug that into cloud darkness threshold. Go figure. G, cloud noise scale. Okay, so now we're looking at noise scale values. So we've got cloud noise scale. This is changing the size of your cloud noise. It's like a master switch for it. because we also have some other scales that we can put in here to affect individual parts of the noise formula, right? Um, then we've got cloud noise offset. This is plugged into right here. So we have a cloud offset and a cloud animation vector slash speed. We take our cloud offset and we hook it into an add node. This is just like a master offset. It changes the starting UV coordinates of your cloud noise. Next, we have a cloud animation vector speed. This determines the direction and the speed at which we will animate the cloud. So right now, by default, I have it on 1.003. You take the XYZ value and you multiply it by the alpha value here, and then you add it to the cloud offset, and that gets plugged into cloud noise offset here. Okay, next, cloud distortion scale weight. So our noise formula has multiple different pieces that you can individually control with these four values. So cloud distortion is basically our domain warping of the master cloud noise function. So right now you can see we have a default of 882 and zero point 0.5. This means that we're stretching it by 8 on the x and y axes and only 2 on the z axis. So that's going to lead to a kind of strandy, horizontally aligned cloud structure. And then we're applying it at zero point 0.5 strength. You could change this to more, you get more distortion. You change this to less, you get less distortion. And then our other three noise controls here are cloud shape scale, cloud detail scale, and cloud micro scale. So the idea here is that your shape scale is going to determine the actual body of the clouds themselves. So in this case, we have our shape scale at 222, and we have its effectiveness at 6. And these are combined in a weighted average. So that means that when we combine this into like our overall function, this would be weighted at a 6. Cloud detail scale is determining what size of noise do we want to kind of break up the shape of the larger shape scale. So in this case, we have 0.5, 0.5, 0.5, and 3. And what that means is that in our composite function, this would have double the impact at 6 that 3 would have here. And then finally, we have microscale, which we have set at 0.03, 0.03, 0.03, and 0.5. That means this is providing very small, fine-grained detail to the clouds, but you will get texture repetition if you make it way too much because you're basically like sampling so small that your noise function would be repeat or your noise texture would be repeating a lot if you were to like turn the weight of this up. So right now, this is 12 times less effective than the shape scale and 6 times less effective than the detail scale. And again, we'll play with all this stuff, and you'll be able to see what the like actual changes in practice that happen. Okay, so each of these are plugged in to cloud distortion scale weight, cloud shape scale weight, cloud detail scale weight, cloud micro scale weight. Next, we have our texture inputs. So we have a cloud volume texture. Inside the engine, if you turn on engine content, I forget where that is, but just look up how do I enable engine content. You will want to look for VT Perlin Worley Balanced, which is a pre-combined engine texture that they use for their clouds, and we're using it for ours as well. You could also build your own volume texture if you have a volume noise library or something like that. But because they already have a Perlin Worley Balanced texture in the engine, I would suggest just using this one. This is a volume texture input, and it plugs into cloud volume texture. Okay, next we have a blue noise texture. We use this to basically erase banding or try to camouflage banding that occurs from doing the ray marching in slices. And this noise texture is basically used to slightly offset every single pixel's ray marching so that they occur at slightly different depths, which stops it from getting the kind of banding. And in here, again, if you go into your textures, just a regular 2D texture. If you go in your textures and you search for blue noise, um, there's a couple. You can use either one you want. You can play with them and figure out which one you like the looks of the best. But this is basically going to control kind of a dithering effect, and that plugs into cloud blue noise texture. Okay, next we have the remaining noise controls. So, uh, like I said, cloud noise scale is our master scale of our noise. If we come up with a good effect here in these, but we don't like the overall scale of it, we can change the scale of everything with this at the same time. Okay, next we got a cloud density floor. This is the cutoff point for when you're sampling the noise. You would say this has no density. This is not in the cloud. Cloud density fall off. This is a fall off factor for the noise as well. These are kind of interrelated. If you increase this, you may have to decrease this. If you increase this, you may have to decrease this. Um, Cloud ambient is what's the darkest the cloud can get, right? And right now we have it at 0.01. So this would be when the cloud is fully in shadow. How much light is it, right? So you can change the darkness on the dark side of the clouds with this feature, with this function or this value. Um, Next we have cloud shadow softness. Cloud shadow softness, even though I spelled this wrong, fix that now. This is probably misnamed a little bit. This is how far do we go when we're fading from the lit part of the clouds to the in shadow part of the clouds. How far is that transition range? And the further it is, the more of a gradual fade into shadow you get. So right now it's set on 0.5. Again, we'll play with all these values when I pull up the material instance, and we can actually mess around with these and see what the actual impact is. Cloud height fall off. This is a value that goes into the cloud height function, and this determines basically how quickly will the tops and bottoms of the clouds kind of fade out. And it plugs into cloud height fall off. All of these are pretty much plugging in. Like, it should be pretty obvious. If you need to pause it to get all these inputs in, then it should be pretty obvious what things need to plug into. Cloud scatter fade. Okay, this function, when you're outside of the atmosphere, it doesn't look right to be applying the atmospheric scattering to the clouds. But when you're inside the clouds, it doesn't look like right for the atmosphere to not affect the clouds. So this function here controls how quickly, as you're going down from entering the atmosphere to the surface of the planet, how quickly does the cloud scattering fade in onto, like, how quickly does the atmospheric scattering fade into the clouds? And that plugs into cloud scatter fade. All right. Next, that covers all the functions that are used to control the cloud layer. Next up, we got the functions that are used to control the atmosphere layer. So first we got atmosphere height. Again, this is how high off the surface of the planet does the atmosphere stretch. So like if I went, you can see that the atmosphere went up. If I go down to 100 again, you can see that it gets smaller. So starting from the surface of the planet, how far till we have no more atmosphere? Next, we have the height of the Rayleigh scattering. So these control the level, like the percentage based height of various scattering effects that go into the atmosphere effect. So you have the height of the Rayleigh effect, the height of the Mie effect, the height of the absorption effect, and well, these would be our three heights of our effects. We have the atmosphere Z offset. So The atmosphere doesn't line up perfectly with the planet by default. This is like a fudge factor that will push the atmosphere towards the center of the planet. And the reason we do that is because if you don't do that, even in the middle, like at 12 noon, if you're standing on the surface of the planet, you would have like the sunset effect all around you because you're at the like that's just the way that the math works out in the function we're using. So we use this to kind of push everything down towards the center of the planet, and that will have you in blue skies at 12 noon, and then you'll get your sunset colors when you're at like the boundaries, like the borders of the where you're transitioning into darkness, right? Okay, now we have our beta values. Pay attention to the values here as defaults. They're important, but you can these are controlling the basically color effect of our various scattering effects. So Raleigh beta, this is spelled wrong. Raleigh beta controls the coloring of our Raleigh scattering, which is the primary scattering that's giving our atmosphere its color. So if we change this, it will change the actual color of the planet, but I'd rather do that in the material instance when we go to look at that. Mie scattering is your basically you're scattering around the sun itself, and so changing this color is generally close to white, but changing this color will change the color of the halo, the light halo from the star itself. Yeah, and then finally, absorption beta. I have it set on this color. I haven't messed around with this too much. And again, I adapted this atmosphere function. But you can mess with this and see what different effects it achieves. And then finally, ambient beta is how bright and what color is the atmosphere when there's no light. So in the shadowed area of the planet, how much how much ambient light is going to be in the atmosphere. All right. Skylight multiplier is what color is our star casting onto the landscape itself. So this adds like some light input into the rendering of the actual ground plane um, of whatever you're rendering this on top of. Also, I should say this is for spherical planets. If you want to do an atmosphere and cloud system, okay, it's two things. This is for spherical planets that you plan on being able to have seamless transitions into and out of. If you aren't planning on leaving the atmosphere or you're not using a spherical planet, I would highly recommend just using the built in atmosphere system that Unreal has because it's good enough for those cases. You don't need all of this stuff that I'm showing here unless you want seamless transitions from ground to space. Um, so yeah, that's it. Like if you just want an atmosphere, use the built-in sky atmosphere, use the built-in clouds. It'll look great. This is really because those don't work super well in a scenario where you want to do a spherical planet and you want a seamless ground to space transition without any artifacting, without any like very obvious shifts in the rendering of the sky atmosphere. Okay, next we got scatter rate divisor. This changes how fast we transition into our fully scattered color. That's too much. By default, we have it set at 0.5. And again, these are plugging into like if you set up all these first, and then you look at setting these up, it'll be pretty obvious where you want to plug them into. But one thing that I should mention here is how all these values are calculated, right? So we have our atmosphere height multiplied by our scatter rate divisor. And then we have our Raleigh beta divided by that value. And that ending value here is what's going to plug into Raleigh beta. So like this is like something that you have to be aware of. You can't just plug the Raleigh beta into the Raleigh beta here. You have to do some operations on it. And likewise, you can't just plug the atmosphere height into the atmosphere radius. You need to take the planet radius. you need to add the atmosphere height to it, and you need to plug that into atmosphere radius. Um, you can, however, plug the atmosphere Z offset straight into the Atmo offset value. Okay, so for each of these scattering coefficients, we're going to have to do the same thing. So we have our scatter rate divisor here, right? And it's multiplied by our atmosphere height. And then it's plugged in to the divisor of every one of our beta values. So we've got Rayleigh beta, Mie beta, absorption beta, ambient beta. All four of these need to be divided by the atmosphere height times the scatter rate divisor. And then they get plugged into Rayleigh beta, Mie beta, absorption beta, and ambient beta over here. Atmo ray beta, Atmo Mie beta, Atmo absorption beta, Atmo ambient beta. All four of these get these values divided by the atmosphere height times the scatter rate divisor. This is going to make it so that when you change the scale of your atmosphere, all of your values stay consistent. If you don't do this, then changing the scale of your atmosphere, because you're changing the scale, you may be stepping through more space, which means that now you are scattering more light, which means that all your colors shift. So this will keep it consistent with the scaling. Okay, next, we've got atmosphere G. That plugs into Atmo G. This is our G scattering value for our atmosphere function. Let's see. We talked about the heights. Absorption fall off rate of our absorption function. Let's see what these are getting multiplied by as well. So yeah, so these are our height values. And again, just going back with what we were saying, these are percentage based. So each of these values can't just plug into height, ray, height, Mie, etc. It needs to be multiplied by our atmosphere height first. So what we're basically saying is that we want our Rayleigh scattering to peak at 4% of our atmosphere height. So that is atmosphere height times height Rayleigh right here, and then plugged into height ray. Likewise, for height Mie, it's going to be height Mie times atmosphere height plugged into height Mie. Likewise, for height absorption times atmosphere height plugged into height absorption. Likewise, for absorption fall off, it's going to be, or no, now we're at a different thing. So absorption fall off 0.4 times our atmosphere height again, and then that plugs into absorption fall off. All right, next, we have our step counts. These are our ray marching step counts for our atmosphere. So we have 32 density steps here and 6 light steps here. And then finally, we talked about the Atmo Z offset, which is kind of pushing everything towards the center. If I put this on 0, it expands outward. If I put it on 0.2, oh, that's 2. If I put it on 0.02, it goes inwards. 0.05 is where we were at. And you want to kind of use this value to place it such that you can see from outside what colors you would be seeing, right? Like we can see that on the surface here, we would have a band of sunset colors. So we don't want that. So we'll go to 0.6. And now we just have blue fading to kind of like the kind of hazy distance color. But then we still have our sunset colors on the borders here. All right. This is an computationally expensive shader, but it does do a very nice job of kind of creating an ambient atmosphere. Finally, once all this is done, you're just going to connect your output to the emissive color output of your cloud atmosphere shader, and make sure that it's a post-process domain again, and that your blendable location is translucency after depth of field. And then once you've done all of that and put all of that together, you should have a functioning cloud atmosphere shader. So let's go play a little bit more with the features of it, which is actually the fun part, right? Like actually messing with it. So the reason that I did this and didn't just use the default built-in stuff is because I was having big issues with being able to get a seamless transition from space to like inside the, I'm slowing it down, space to inside the atmosphere that looked good. It would kind of, the effect would change as you approach the surface, as you exited into space. The clouds don't look good from outside the planet. If you go too far away, the clouds disappear, things like this. But with this shader, you can go down to the surface, look around, see your clouds and whatnot. You can go up into space, and everything's volumetric. And at no point do I get like a jarring change in the way everything is looking or anything like that. And you can also kind of see the planetary shadow occurring in the clouds here. We can actually look at it um, from down here as well. You can see that like the shadow cone of the planet is affecting the clouds. And we can also see that as we approach the surface, our atmospheric scattering is also affecting the cloud, which is that scatter rate that we talked about earlier. So let's come back out here and let's take a look at just kind of messing around with the HLSL shader here. We're going to change this to unlit because, again, it's a very expensive shader, but it does a lot of jobs. So even though it's expensive, for me, I think it's going to be worth it. You just have to be a little careful with trying to do too many more post-process shaders at the same time, right? So what do we got? We'll just go through each one of these functions and change it, and we can look at what happens when we do. So first, we got atmosphere height. Atmosphere height controls the atmosphere height. Go figure, right? Like, if you want a big, thick kind of atmosphere, you could do it that way. If you want a thinner atmosphere, you can make it smaller. For now, we'll just put it back to around where it was. Atmosphere Z offset pushes the atmosphere towards the center of the planet. So as I do this, you can see it going towards the center of the planet. As I do this, you can see it coming out. And if you go too far, it'll get all jacked up. So you don't want to do that. You want to make sure, usually you want to look at the colors here, and at whatever the side of the most lit planet, you want it to be like in this bottom range of blue. So we'll just go ahead and do that. I think that looks pretty good. So we'll do 0.03 here, and we're good. Height Raleigh and height Mie, these control the, again, the height of these scattering effects. So if I turn height Raleigh up, our Raleigh scattering moves up. And our atmosphere is actually very thick right now, which if is an effect that I kind of liked. But if you wanted a thinner atmosphere that's a more discrete bubble, you could actually turn this down, but then increase the height Raleigh, and we'll just. And so these are kind of related to each other, right? But I don't want that. I don't want that either. That's too big. Let's turn this back to 0.06. So, like, again, you can kind of mess with these values and get a feel for what you like. So, for me, I feel like that looks pretty good. Height Mie is changing the height of the Mie scattering effect, which again is our basically light scattering around the point. Usually, you can have a pretty solid guess that it's going to be about half of whatever your height Raleigh is. And I'll show you what that does. So like this scattering we're getting here is driven by the Mie. The scattering are like around the light itself. So where like the light gets thicker in the atmosphere here is being driven by that. The sun is got its own post-process lens flare shader going on here. but you can also use the built-in lens flare. I didn't, it seemed pretty low res, but that is not the topic of this video, so I'll just mention that we are also running a post-process lens flare for the sun, and we'll move on. Height absorption. This controls the height of the absorption effect. You can kind of see what happens as I change this. By default, is set to 3. I feel like that does a pretty good job. You can mess around with all these values and figure out what you like and what you don't. Scatter rate divisor. This changes the rate of scattering, like how quickly the light scatters inside the atmosphere. Again, we'll set it at 0.5. Seems pretty decent. Atmosphere G doesn't seem to have too much of an effect. I'm not actually certain this is still being used, but I would plug it in anyway. Absorption fall off. How quickly does our absorption take place? It's set by default to 0.4. I think it's pretty good. All right, so now we get into the good stuff. Rayleigh beta is our Rayleigh scattering coefficients. This is how you change the color of the atmosphere, basically. You can mess with these numbers, but I would suggest leaving them and just dragging around on the color wheel here, but not changing the intensities of these values. And you'll notice that because we're using actual scattering equations, when we do that, the scattered light color here changes as well. So like at blue, the more blue we get, the more yellow our scattered light is. When we're at like an actual kind of sky color, we get Earth-like sunsets. If we were to go into pink, we would get green scattered light. If we go into red, we start to get more blue scattered light, orange into deep blue, green into kind of purpley, right? Teal into like this kind of pinkish red. So changing this changes the whole appearance of the atmosphere. The Mie color scattering, uh, I don't usually change this, but it has to do with the scattering around the sun itself. Let's go in the atmosphere. You can see this is changing like basically the halo of scattered light around the sun. So if you had a planet that you wanted a very colorful star or something like that, you could potentially enhance that by changing the Mie beta here. Absorption beta, um, changes the absorption coefficients. You can play with it. I wouldn't be able to tell you exactly what's going on here, but if you fuck with the colors, you'll see that it kind of changes around the overall look and feel. And then ambient beta is what is giving us a glow on the dark side of the planet. So right now we're at 0.1.1.04. Let's try bumping that up to 0.3, 0.3. Okay, that's still probably too small for us to see in effect. 3.3, 0.3, 1, 1, 1. Alright, so if I go down to the surface here, you see this kind of halo around the surface of the planet. That's being driven by this ambient color here. So if I change this, the ambient color becomes a bluer color. If I change this, it becomes a redder color. But for now, we'll probably put it at like 05, 05, 1. Just a very subtle ambient color around the skyline, right? The other nice thing about this cloud function is that they're truly opaque, which I had problems with for a while getting that to work properly. But the clouds are opaque, and they will partially or fully, depending on where you're at and how thick they are, obscure the night sky. Um, yeah. Okay. Great. So save that. Skylight multiplier. The best way I can put this is you want something that's like a faded down color from whatever color of the star you're at. So, for example, if we had, say, a green star, We could go to green and change the intensity of how the light color contributes to the planet's surface, right? Cancel that, leave it as at its default. And then next we have these two atmosphere density steps and atmosphere light steps. You won't probably tell a huge difference in these until you get to low step values. So we were at 32, 16, 8, 2, right? 1. You don't want to just do 1 because it looks like trash. And you don't want to do 6 because it still looks like trash. And 8 is starting to be acceptable. 12, 16, 32. I set it on 32. You could probably get away with 16 if we're being completely honest. And then likewise, the cloud light steps. 1 doesn't look very good. 2 starts to look better. 3, 4, 5, 6, 7, 8, 9, 10. Once you get past like 8, you kind of stop seeing a difference. 16, right? 8, 16, 8, 6. So I have it set to 6. These are your number one. The steps, the density and light steps here, and the density and light steps in your cloud shader are the number one way that you can make the shader more performant at the cost of fidelity. So we'll leave it at 16 and 6 because I don't think that looks terrible. Let's go down to the surface real quick and make sure that it doesn't mess that up either, though. No, it still looks pretty good. All right, we're good. So next, let's do this. All right. Next up, let's talk about the cloud settings. All right, first of all, the most obvious one, cloud color. We can change the color of the master color that goes into the clouds. Generally speaking, you're going to want something in the near white range, but if you wanted tinted clouds because of like some chemical composition, or you just wanted to go full like nuclear radiation clouds, you can do that. All right, great. Cloud color, pretty simple. Cloud height. Okay, this is the height off the planet that our cloud layer starts. So let's actually copy this value before I start messing with it because I like kind of where it's at. So this changes our cloud shell. Now be careful because we have a maximum limit we can trace. You can see where they're fading out here. So you generally want to have the cloud height set so that would occur behind the planet. And then the other kind of tricky thing to keep in mind here is that this shader is very, very expensive, but we cull any samples that would occur behind things in the scene, which includes the planet. So because we cull things that are behind the planet, when we're right here, we're actually only having to render about half of the total samples that we would render if there was no planet here because we're obscuring most of the backside of this. But as you increase this, more and more of the cloud is in view and it slows the shader down a lot. And you can see it kind of chugging along and then getting smoother as we get closer to the surface of the planet, right? So, and then also, because the light cone is actually based on the planet scale, as you get bigger, you'll have more areas in light. So let's get it back down to where it was. Well, we could actually go a little bit under that. Maybe like right here, okay? Cloud thickness. Okay, this is the thickness of the cloud layer. So if we increase cloud thickness, our clouds get thicker. But you also have to be careful here because, again, we're working with samples. So the thinner the area we have to sample, the more samples get crammed into that thinner slice. So as we make it thicker, our quality decreases because we're getting less samples in a larger area. Or we're getting the same amount of samples, but it's in a larger area, right? So we'll just go down to kind of a nice thin cloud layer here. Next we have cloud density steps. Um, This increases cloud quality at the expense of making it a lot more expensive. Uh, so this is changing the number of density steps. We're doing an array march loop for the clouds. Uh, so we'll cut that back down to 32. I would suggest leaving them at 32 and 3. This seems to work pretty well. If I change it to 6 or 12, you can see it starts changing things. I would suggest leaving it like this. You can mess around with it. I don't think it's like those values are pretty dialed in. All right, and then this is the number of steps that we're using to calculate the cloud lighting. So at 1, our clouds look like this: 2, 3, 4, 5, 6, 7, 8, 9. So you can see by experimentation, after about 6, we stop seeing changes. So at 5, 6, minorly perceptible change. 4, 6, pretty clear change. 46, almost no change from 6. So I would suggest 6 seems to work pretty well. We have our absorption functions. You can just mess with these and see what they do. Absorption to cloud and absorption to light are changing basically the perspective of, like, I'm trying to think of a good way to describe this. Um, this is an absorption, so like inside the cloud going to the light, what's our absorption? And then this is outside the cloud going to the point in the cloud, what's our absorption? I guess would be the best way I could say this. But point 7 and point 3 seem to work pretty well. Cloud G, this changes the direction of the asymmetric scattering. So we have it set to point 5 here. You can see that you don't want to go above 1. Um, Also, you probably don't want to go above, like, I would say point 0.7 looks fine, but point 0.8 doesn't. So about point 0.7 is probably as high as you want to push this. Um, point 0.3 will cause your clouds to be lighter on top as you go under point 0.5. At point 0.5 is perfectly balanced. Um, we can look at what effect this has from underneath. So I would say like a point 0.5 is usually pretty solid for this. You get a nice blend of attributes. All right, great. Cloud darkness threshold. So the best way to understand this is to just play with it. It changes the light slash darkness of our clouds. You probably don't want to go to 0 because it just becomes black, right? But this is controlling like the shadowed area of your clouds. So I think that we have it set to like what, point 0.5 here. You could probably go like point 0.4 or point 0.3 just fine. I wouldn't do 0. I probably wouldn't do like point 0.1. Point 0.3 to point 0.5 is probably fine. All right, cloud noise scale. This is an easy one to understand. We change this, everything gets bigger. It's the same overall formula that we were using, but on a much larger scale. Likewise, we bring this down, everything gets smaller, um, and smaller and smaller. But like at some point, you're going to see tiling. You don't want that. So I would suggest just, mess around with it, find something you think that looks good. Cloud density 4. This is our basically our cutoff point for what is in a cloud and what is not in a cloud. Um, you could say if you wanted to have a stormy time on your planet, you could decrease this to have more cloud cover or increase it to have clearer skies. Likewise, cloud density fall off functions in a similar way, but not exactly the same. This affects like the actual fading on the edges of the clouds, whereas the floor is just a direct cutoff. But like, let's say we go down to a much lower floor, but a much higher density fall off, you will still get, it's got more of like a fade range when you do it like this. By default, I have it set to 0.5 and 4, and that produces this. Okay, next we have all of our different scales for our noise. So this is our domain warping. You can kind of see as we change these, we're changing the scale of the domain warp that's being run on the overall effect. Generally speaking, I have it set on 8, 8, and 2, which yields this kind of horizontally banded clouds. And then we can also increase the intensity of the domain warping or decrease it. If we set it to 0, then this would be completely non-warped. If we set it back to 0.5, you can see the effect. Shape, scale, weight. All right. This changes the scale of the actual clouds, and you can change it on all axes, but generally this one is just evenly spaced. So you could just do like 10 if you want to make them bigger. You can do 2, 1, 0.1 if you want to make them smaller. And you can kind of see the effect in practice here as we change those values. So I think we were on 2. I think that looks pretty good. We can also change the overall weight of the application here. So like if I change this to 16, our clouds get smoother because we're applying more uh, precedence to this than our other noises by a substantial amount. If I put this to 1, now our other noise, like our detail and micro noises, are having a much greater effect because this is having a lower effect. It was set to 6, so we'll leave it on 6. Okay, cloud detail scale. So this is a next level down. Um, we could say reduce this scale if we want more micro variance, or increase it if we want larger variance from this. So like, let's do 2. 1.5. I found that 0.5 works pretty good. And again, this is our weight. So if I decrease this, we have less effect from it. If I increase it to the same as our shape, it would have an equal impact. Increase it more, you can just kind of see what happens as we change this number. Various portions of the noise take over. And microscale weight, this is, well, first let's put it to 0 and you'll be able to see. Okay, so this is basically how are we breaking up the clouds on a very fine scale. So 0.5, you can see our little kind of fluffiness of the clouds comes into play here. If we increase this, eventually it looks really bad because we're weighting this enough to where now you're seeing the repetition in our micro scale because we're having to get this fine of detail, we're having to repeat our noise a lot. So we don't want to have this be very high weight, but if we have it be a low weight, then it will break up our other noise patterns pretty nice. All right, next, cloud offset. So this is basically just moving our sample around, or the baseline for our sample around. So with this, we can shift the point at which we start sampling all our noises. It doesn't really matter that much, to be completely honest, unless you have something very specific in mind. Cloud ambient. If I set this to 0, we don't get any clouds on the dark side of the planet. At 0.01, it looks like this. At 1, it looks like this. At 0.1, it looks like this. 0.05, it looks like this. 0.02, it looks like this. 0.01, 0.005, etc. You get the idea. This controls the darkest side of the clouds. I feel like 0.01 usually looks pretty good. All right, cloud animation vector. This is the direction that our clouds will animate and the speed at which they'll animate on that direction. So you don't actually, if you set this to 0, we'll have no animation. If we were to set it to 1, we would have very, very quick animation. And if we change this the texture will scroll in different directions. All right. And you could animate this over, you could animate the value, like the direction the clouds are moving over time, or you could come up with a stronger or a more in-depth animation sequence. But basically, this controls the animation of the clouds. So if we go down to the surface here, we can kind of see what that looks like. Obviously, this is drastically sped up so that you can kind of get an idea of what's going on. In reality, it would be something more like this. And even this is very sped up over what you would actually want to use in practice. But um, yeah, I mean, you can see the clouds kind of moving around and doing stuff. So we'll go back to 0.001. Now they're probably moving about the speed of actual clouds. Okay, so that's our animation factor. We're just gonna reset this guy. All right, we can kind of see him getting animated. Cloud shadow softness. This is the rate of change of the shadowed portion of the clouds. If we turn this up, it takes longer for our clouds to fade out into the shadowed area. If we turn it to 0, then you just have a hard cutoff line where the shadow cone is, which you probably don't want. So something around the like zero point 0.2 range, 0.1, 0.5, 0.2 seems to be about the sweet spot here. Cloud height fall off. Okay, let's just take a look at what this does. So look at this cloud from the side. If I decrease cloud height fall off, it gets thicker on both the top and bottom. And if I increase cloud height fall off, it gets thinner until it's very thin. But generally speaking, it seems to be about like a 0.03, 0.05 kind of field. You just set it to that and it'll be pretty good. Um, oh, and then finally we got cloud scatter fade. Let's take a look at what that does. So as we enter the atmosphere here, the clouds will start to take on some of the scattered color of the atmosphere itself. So let's go up towards it. It starts fading back into just white, fading back into just white until a certain point at which I enter the cloud atmosphere layer and it's just completely white. But as we get closer to the bottom, we incorporate more of the scattering of the sky itself, the atmosphere onto the clouds. So if I increase this, this is a field that can be used to both change the range at which this fade-in occurs or completely get rid of it. If you want to just white clouds, you make this a really high number. You're not going to get very much scattering on the clouds. You want the full effect, then you'll need to bring this number down to something. And what this effectively is after you cross the boundary of the lower cloud barrier and start heading towards the planet, what percentage of the thickness of the atmosphere do you have to travel through before you're seeing the fully scattered atmosphere color on the cloud color? So in this case, we'd be about a third of the, once you've traveled about a third of the atmosphere depth, you would have the full color contribution from the atmosphere. And so we'll just take this down, which also means that at a certain point, it's just going to be that color, right? Like it doesn't get any more intense from that point. And we have a very small value here, so it's going to transition very quickly when we get close to the cloud boundary, which we should be able to see. Yep, there it is. So with it set to 0.03 or 3%, we transition this quickly. With it on like a 0.2, which is what it was on, we have a more gradual transition to the colors. So about zero point 0.2 seems to be about right. Over here, we can play with our different noise textures. I wouldn't recommend changing these from the ones that I've suggested here, but if you have volume noise, you could try other volume noise textures. T. Let me find one. VT gradient. Let's try gradient turbulence. There you go. We have different kinds of clouds now, right? And you also will probably need to mess with some of the other settings to get it to look right, because it's really made to use the one that we were just talking about, which is why it's kind of jacked up here. But we'll change it back to the Pearl and Whirly balanced. Blue noise texture, I would suggest taking either of these blue noise textures. It doesn't really matter. Um, they're both just doing the same functionality, or the same, they both serve the same purpose. All right. Next, we have our shared parameters: planet position, planet radius, light position, light intensity. Um, the only one here that really would be of concern would be light intensity, right? Obviously, you increase that, you increase the lightness. I think we're on what, 10? And we got like nice sunset colors here. Nice transitions going from lit parts to unlit parts of the planet. If we wanted to hop down here and kind of explore around on our planet at sunset. Oh, nope, we crashed. Eddie. Oh, he's going to freak out. All right, well, hold on. I'm still working out the last kinks in the mesh system, but okay, we'll start it back up. So anyway, that kind of covers the features of it and how you mess around with it. Um, I'm gonna upload this as a video. I'm gonna place the code in the description of the video, the code for the feature, or the code for the custom node. The rest of it is kind of just groundwork for basically setting up the material, adding all the inputs so that they match the inputs in the atmosphere shader, and that's it. We'll just go in and kind of play around with it. Unfortunately, the mesh rendering pipeline bug is still there, and I haven't managed to figure it out yet. Oh, hello, guys. Welcome. Uh, there we go. Everything loaded in. Load our editors back up. So the end goal is to be able to kind of proceduralize all this so that I don't have to set these values manually. It just be generated along with the planet mesh and all of the other stuff. Right now I'm tuning it all by hand, but we can kind of see the effect here as we go around the Earth or the planet. Um, and yeah, so I think that pretty much covers it. I also added everything into, logical groups here: atmosphere parameters, cloud parameters, shared parameters. Um, just real quick, one more time to give some zoomed in views of the fields that have to be set here. Screen UV, camera position, camera vector, planet position, light intensity, planet radius, scene depth, world position, pixel normal, scene color, cloud height, cloud thickness, cloud step scale, cloud density steps, cloud light steps, cloud absorption to cloud absorption to light, cloud darkness threshold, cloud G, cloud ambient, cloud shadow softness, cloud noise scale, cloud noise offset, cloud distortion scale weight, cloud shape scale weight, cloud detail scale weight, cloud microscale weight, cloud volume texture, cloud blue noise texture, cloud density fall off, cloud density floor, cloud height fall off, atmo thickness, atmo ray beta, atmo mie beta, atmo absorption beta, atmo ambient beta, atmo G, atmo height ray, atmo height mie, atmo height absorption, atmo absorption fall off, atmo skylight multiplier, atmo density steps, atmo light steps, atmo offset, cloud scatter fade. Then you have the code that you would paste in. I'm going to paste that when I push this on YouTube. I'm going to put that the code in the comments. We also looked at it earlier. Here's this block. I'll try to zoom out a little bit so that you can also see which fields they're plugged into. These are derived and shared parameters. These are our cloud parameters. Offset, animation vector speed. Multiply the alpha value here by the time field. Multiply that by the RGB. Add it to the cloud offset. Plug it into the cloud noise offset. There are various float 4, detail, distortion, shape, detail, and micro scale weights. Our volume textures, all of our scalar textures. And then remember to make sure and do things like adding the planet radius to the atmosphere height when determining the atmosphere radius. Um, Multiplying the scatter rate divisor by the atmosphere height and dividing it by all of our beta inputs. And then likewise, multiplying the atmosphere height times our various height values to feed into our actual height values for our various types of scattering. Um, yep. And then finally, our absorption fall off is multiplied by the atmosphere height again, and then plugged into our absorption fall off. And the reason we do this is so that when you change the scale, like you made this twice as big or half as big, all of these values stay consistent instead of like having to manually hand tune it for each one, right? We want it to be a proportion of our scale rather than just a hard coded value. And then again, this is like your light cast on the surface of the planet, your ambient light, your absorption beta changes the color of absorption. Your Mie beta changes the color of like your light halo around the star. Your Raleigh beta changes the color of the atmosphere itself. And then you just have the rest of the stuff, scalar values and whatnot. All of that gets plugged into these inputs. If you're confused about an input or like something's not working, you can always go here to where the struct is configured and look at the actual values that are getting passed in. One thing I will say, uh, this is negated because we need the flipped vector in all our calculations. So just realize that this is slightly different than what's getting passed in. Some of these are derived, like we don't pass in light direction, we just pass in the light position and we derive the light direction. What else is derived here? Uh, Cloud min and max radius are derived using the planet radius, cloud minimum radius plus the thickness. And yeah, so I think that pretty much covers it. We can kind of just go down to the surface of the planet and let's see if we can actually walk on the surface here without crashing this time. There is some work that I still need to do. Like this is not a finished thing. You can see it actually. One of the major problems here is that until your character model is close to it, it will overlap. I think to fix this, you would basically create a custom depth stencil for your character. So you would want to render this to the custom depth buffer, and then you could utilize that to kind of mask out the post process effect. Haven't done that yet. Once you get close to it, in fact, we're gonna be falling forever like this. Let's get a little bit closer to the surface. All right, there we go. But yeah, so it's not a replacement for the built-in sky atmosphere. You can still use that if you don't need to be able to fly in and out of the atmosphere and go seamlessly from space to ground, but you're just entirely happening on the ground. I would I would highly suggest just using the built-in stuff. There's no reason to use this in that case. The only reason that to use this is if you want to seamlessly be able to enter and exit the planet atmosphere in like a spaceship or something like that. And then if you've ever tried to do that with the built-in sky atmosphere and cloud stuff, you will quickly realize that there's a bunch of um, issues and kind of idiosyncrasies with inconsistencies in the appearance of it as you traverse through different layers of the atmosphere. In particular, the clouds, uh, when you get a certain distance away, will start disappearing in a very like jarring manner that doesn't really look very good at all. So yeah, but we just fall down here to the planet's surface, and then we can kind of walk around on our procedural planet here, and we kind of see all of our clouds off there in the distance, our sunset view, run around on the surface, and I'll have our little dude running off into the sunset, and I think I'll call it here, and I'll probably go play some Magic. So later, guys. Hopefully this was helpful, and I'll talk to you later.